Okay, in the last lecture, we learned about multidimensional scaling. MDS. Okay, in multidimensional scaling, we had n data points in d-dimensional space. I can represent them in a matrix of d by n. And the goal was to map them in lower dimensional space in p-dimensional space. The approach of multidimensional scaling, or to be more precise, metric multidimensional scaling, is to compute the pairwise distances between all points in domain X and try to find a configuration in Y domain such that the pairwise distances in Y domain is as close as possible to pairwise distances in X domain. So that was the problem that at the first place we tried to solve, and we learned that the final solution is lambda hat square root times V transpose, where lambda hat is diagonal matrix such that diagonal values are eigenvalues of X transpose X, and basically are the top P. Diagonal values are the top P eigenvalues of X transpose X, and V is a matrix of eigenvectors of X transpose X. So that's what we learned in the previous lecture. So clearly, this solution is identical to dual PCA. If you remember in dual PCA, in direct PCA, Y was U transpose X, when U was eigenvectors of X transpose. In dual PCA, Y was sigma V transpose, when V was eigenvectors of X transpose X. This is eigenvectors of X transpose X. And sigma was the matrix that we computed from singular value decomposition that are basically singular values on the diagonal. And singular values are basically a square root of eigenvalues. Okay? So the solution to MDS is identical to the solution of dual PCA. It means that if you do PCA on a data, you have preserved the pairwise distances. PCA has many properties. One property that we talked about was that principal components are in the direction of maximum variation. Another property of PCA, which you have seen in your assignment, is that it gives the best reconstruction. If you want to find a subspace such that you want to project all data points on that subspace and then project it back the solution would be PCA. So PCA is optimal in a sense of finding subspaces that gives the best reconstruction error, minimum reconstruction error. So here we see another property of PCA. So PCA preserves pairwise distances. So if you want to go from dimension 10 to 2, and your concern is to preserve pairwise distances as much as possible, then your solution is PCA or MDS. But the solution is MDS as long as this distance is Euclidean distance. So MDS, in a sense, is more general. In PCA, we just work with Euclidean distance. As long as the distance that we are measuring, the pairwise distance between points, is Euclidean distance, then the solution of MDS is identical to PCA. But this distance could be a different thing. Could be something rather than Euclidean distance, and still MDS works. So today, actually, I'm going to introduce a new algorithm to you, which is called Isomap. So far, all dimensionality reduction algorithms that we talked about are taking care of subspaces. So the assumption is that data is on a subspace. Okay. So you can easily see that MDS is also linear. One way to see that is by appreciating the fact that this is identical to PCA, but also you can intuitively see that this is linear. You know, if these points are in three-dimensional space, and I would like to preserve pairwise distances, Euclidean pairwise distances. You know, the distance between these 2 points, for example, in Euclidean space, in linear case or in nonlinear case, the Euclidean distance between these 2 points will not change. Okay? But what about the distance between 2 points that are far apart? Look at the red line here. This is the Euclidean distance between these 2 points, right? But if data is not on a subspace and it's on a submanifold, then what is the Euclidean distance between these 2 points? You know, the Euclidean distance between these 2 points would be just this short line, right? This is not the distance that we measured here. So the Euclidean distance, if we have a curvature here, is much shorter, right? So as long as the data is on a subspace, MDS is going to do a good job like PCA. But if data is on a submanifold, then MDS is not going to do a good job, because MDS is going to measure the Euclidean distance between these 2 points here, and it's going to preserve the same distance in low dimensional space. It's as if all of these points are collapsed, you know, all of this manifold totally are projected on a subspace. So it doesn't capture the curvature, it doesn't capture the geometry of the data nicely. So it has been an open question since the time that we knew the solution of PCA and MDS, which is about 100 years ago. It was an open question that how we can address the problem in the case that the data is not on a subspace. And there has been a couple of sort of partial solution to this problem. But good solutions to this problem, which was basically a point that interest in nonlinear dimensionality reduction renewed again, was 2001, when 2 papers published at the same issue of Science paper back to back. One of them was Isomap, and the other one was LLE, Locally Linear Embedding, that we are going to talk about that one also today. So Isomap was a solution to nonlinear cases. It is basically, Isomap is basically MDS. When you change Euclidean distance to geodesic distance. Okay, it was quite wise, but a very, a very wise but a small contribution to the problem. So suppose that, I'm looking at the distance between two cities on the Earth, right? There's a city here on the Earth, and there's another city here on the Earth. And you want to travel from one city to another city. So what are you going to do? This is not a valid distance between these 2 points. If you ask me how can I go from here to LA, and if I measure the Euclidean distance on the Earth between Waterloo and LA, this is not basically, the way that you're going to travel. You are going to travel on the on the surface of Earth, right? And the distance that you're looking for is this distance, rather than this distance. This is Euclidean distance. This is geodesic distance. Okay? So, in Isomap, we replace Euclidean distance with geodesic distance. Okay, so that's the only difference. How can we compute the geodesic distance between 2 points? If you know the manifold already, so we can compute the geodesic distance between 2 points, basically the distance on the manifold, rather than the shortest path between these 2 points. But in the case of dimensionality reduction, the only thing that I have is this n data points. I don't have the manifold. I don't have the surface. Yes?
What is that non-Euclidean distance called? The
geodesic distance. This is roughly the distance on the surface, on the manifold, rather than the shortest path between these 2 points. Okay, if I know this curvature, I'm fine, I can find the geodesic distance. But in the case that we are dealing with, the only thing that I have is n data points, right? I don't know anything else. I don't know the manifold. I don't know the geometry of the manifold. But let me get back to this example. Suppose that I want to travel from city A to city B. Okay, one way to measure the distance between city A and city B is to find its closest city to A. Okay, let me call this closest city to A C1. And measure the distance between these 2 cities. In this case, just measure the Euclidean distance. If I'm pretty close to A, there is no difference between Euclidean distance and geodesic distance, because if I go from Waterloo to Kitchener, then I can ignore the curvature of surface. I can ignore the curvature of Earth. It's almost linear. So Euclidean distance between these 2 cities are almost the same as geodesic distance between these 2, because the effect of this curvature is almost negligible. So suppose that I measure this distance. Then when I'm on C1, I can find the closest city to C1, call it C2, and measure the distance. And then find the closest city to CC and measure the distance. And I can repeat this process by finding the closest city to each city and then add up the Euclidean distance of all of these and claim that the geodesic distance between A and B approximately is summation of Euclidean distances here. Okay? In fact, in graph theory, that's the way to estimate the geodesic distance between 2 points. You know, if you have a graph from point A, from node A on the graph to node B on the graph, if you find the shortest path, in a sense that if I want to go from point A to point B, what is the shortest path between these 2 points? The shortest path, there are different algorithms, and on the daily basis, we are using these algorithms. You know, you are using GPS to travel from one city to another city, and there's a huge graph here in the GPS. When we want to go from one city to another city, GPS is going to find the shortest path on the graph between these two. Okay, so shortest path could be an estimation of geodesic distance. So let me show you this slide here. Suppose that these are the points that I have. I explained to you that Euclidean distance between these 2 points is this short line, but that's not what we are looking for. We are looking for this distance because we would like to unfold this manifold on the low-dimensional space. So what I want to preserve between these 2 points in low-dimensional space when I'm unfolding this manifold is this distance, which is called geodesic distance. So to estimate geodesic distance, I can make a graph out of this data. How can I make a graph? I can make, for example, a k-nearest neighbor graph. I can connect each point to its k-nearest neighbor. Find the k-nearest neighbor of the point and connect this point to those points. And then I have a graph. This is a graph. See, each point has been connected to its k-nearest neighbor. On this k-nearest neighbor graph, then I can compute the shortest path between these 2 nodes. The shortest path between these 2 nodes basically is this red line on the graph. The geodesic distance is blue line. They are not exactly the same, but this is a good estimation of the geodesic distance. So I'm going to compute geodesic distance between all points and replace it with Euclidean distance. Yes?
I understand on the manifold that the geodesic distance is important for between points.
Mm-hmm.
But some sort of information is being captured by that Euclidean distance as well, right? Like on top of the manifold, that distance is important. Why do we ignore that Euclidean distance?
What information is captured by that Euclidean distance?
I'm not too sure, but just visually, like that's even more information about the 2 points. Like the geodesic distance is that much, and the Euclidean distance is that much. Why don't we consider the Euclidean distance to begin with?
You know, don't forget the task. You know, the task is unfolding, right? This is what I want to do. The task is unfolding, and my approach is distances. The distances that are going to be preserved are local distances. So geometry of the manifold will locally be preserved.
So it's all local.
All local, because locally, you know, you can assume that points are locally on a linear patch.
Yeah.
But globally, this is not true. There is a curvature here. And Euclidean distance does not capture the curvature. But it does capture the geometry of the points locally. So basically, if I have a k-nearest neighbor graph, on my k-nearest neighbor, I can assume that distances are correct. But globally, I can't make this assumption. So definitely, this Euclidean distance that you're mentioning between those 2 points, capturing some information, right? But don't forget the goal. What is the goal? What do we want to do? In terms of our task, which is unfolding, that Euclidean distance is not important. If this is the manifold, or if this is the manifold, or this is the manifold, which change the Euclidean distance between these 2 points, I don't care. Still, I want to unfold it and see this, right? So Euclidean distance between far apart points will be irrelevant in this case. Yes?
So this algorithm would be like incredibly slow to compute, right?
Yes.
For every just like this, like 01 or something, something huge.
Right. Yes, it is incredibly slow. Right. But don't forget that this is the first solution to the problem. It was a breakthrough published in Science, right? 100 years we had no solution. All of a sudden we had 2 solutions in the same issue of Science, right? It was the first solution. Yeah, it is slow. It can be used for toy examples. So if you have more than a couple of thousand points, it's not going to work. There are variations of that to speed it up, like landmark, Isomap, and so on, which are choosing some points and estimate other points using those points to speed it up. But at the moment that we are talking, we have methods way more accurate and way more robust and way more fast in terms of computation. But that was the first solution, right? Yes?
What is figure C exactly saying? Or what are the axes on figure C?
C?
Yes.
Here? It's nothing. It's just this one, the data points when you made a k-nearest neighbor graph out of that. So C is basically just a label when they wanted to, this is from the paper. When they wanted to refer to this, they said in C. C is not a variable here. It's just the title of this graph.
No, I understand. But I'm saying the axes.
Yeah, the axes are basically, these are 3-dimensional points. X, Y, and Z on 3-dimensional spaces. So these axes are X, Y, and Z in 3-dimensional space.
And in figure C,
The same. Yeah. X, Y, so you don't change the geometry of the data. That's your data. The only thing that you do, the only difference between B and C is that you connect each point to its k-nearest neighbor, and you get C. So it's still these axes are 3 measurements that you have for each point. Okay, so is that clear? So Isomap basically has 3 steps. Step 1, construct a k nearest neighbor graph on n data points. So simply choose a k. This k is going to be a parameter of Isomap. That's a parameter of the algorithm. You have to choose k. You have to decide that k is 2 or 10 or 200. So you're going to connect basically each point to its k nearest neighbors. That's the first step. Step 2 is to compute shortest path between all points as an estimation of geodesic distance. Call it dg. Okay. 3. So this is, from now on, it's Isomap. In Isomap, we had this distance, but we computed k, which was minus 1/2 h dh, and that was dx in Isomap. Now it's dg. Yes.
Does such decomposition always exist?
Good point. I will talk about this. If I forget, just remind me, because it's an important point. Yes.
And that step 2, that estimation, that's using the Euclidean distance between the
Yeah.
intermediate.
Yes. True. And there are a standard algorithm which has been known from long time ago in graph theory to find the shortest path between 2 points and to estimate geodesic distance. So k, we compute this k, then find eigenvectors of k and call it matrix V. Find eigenvalue, the top P eigenvalues of K and form lambda hat. Then the solution would be lambda hat square root V transpose. That's our low dimensional representation of the data. Yes?
What is H again?
H is a centering matrix, which was constant and can be computed as I identity minus 1 over n E transpose when E was 1, 1, 1, 1, n by 1. So this is n by n matrix of 1, 1, 1. It's centering matrix, basically HD. H double centers D, as if you're summing up all rows and find the mean and subtract it, find all of the summation of columns, find the mean and subtract it. You're centering D from both sides. Okay? So getting back to your question, does this decomposition always exist? It does exist. You can decompose K, but there is no guarantee that K is positive semi-definite. If you take a look at the theorem that I presented in the other day when I was talking about MDS, the theorem explicitly says this correspondence between positive semi-definite matrices and Euclidean distances. If distance is not Euclidean, there is no reason that this K is positive semi-definite. What is wrong if this is not positive semi-definite? If this is not positive semi-definite, it means that it cannot be decomposed in the form of X transpose X. In other words, it cannot be embedded in a Euclidean space. It means that there does not exist such configuration that you can present. So what's going to happen in this case? It's possible that we compute geodesic distance, we compute this K, and then K is not positive semi-definite. So it means that there is no configuration in p-dimensional space to preserve this. So in this case, actually, what we are going to do is to project this K and the cone of positive semi-definite matrices means find the closest positive semi-definite matrix to this K and then decompose it. It's not, if you look at the original paper in Science, they even didn't mention that, you know. If you look at their code, when they want to do eigs of K, if K is not positive semi-definite, it means that it could have imaginary part. It could have negative values, right? They just put absolute value in front of this eigs function. So one way to project a matrix which is not positive semi-definite and the cone of positive semi-definite matrix is to get rid of imaginary part, is to get rid of negative values. Knock down those negative values. But they didn't mention that in the original paper. But after that, people realized that it's important in that line of code, actually. It's basically projection. Okay, any question? Okay, let me show you a couple of examples. This is an example in the original paper. This data set has 3 degrees of freedom because it has been created, the data set has been created manually. This object, you know, we had this object and we had camera rotating on the horizontal axis, taking pictures of this object. A camera has been rotated on the vertical axis, taking picture of this, and the light has been changed, illumination has been changed. So if you look at the x-axis, it captures this variation of data, I mean horizontal rotation of the camera. So on the left, you have left sidal view, and the right, you have right sidal view. And if you look at the y-axis, it captures the rotation of the camera on the vertical axis. And there's another degree of freedom which has to do with illumination. If you apply PCA on this data, you're gonna get a good result. You know, it's not nice like this one because the data is not on a subspace, so it's way nicer than the result of PCA. Okay. Here is another example of the original paper. One axis captures this variation related to loop at the bottom of these handwritten digits, and the other one has to do with the curvature at the top of these handwritten digits. They also showed this data set, some illustration of this data set, that one axis captures like extensions of the hand and the other one shows rotations. Any question? Yes?
And that's like the result of Isomap?
That's the result of Isomap.
So there's some data set with a bunch of these images and we ran Isomap.
Mm-hmm.
A lot of those plot images.
Mm-hmm.
That's what we did.
Right. Yes.
Can Isomap work on surfaces?
Sorry?
Can Isomap work on non-smooth surfaces?
Non-smooth surfaces?
Yeah. There's, I mean, the example that you showed us, the Swiss roll. Like,
Yeah, non-linear.
I mean, not, I mean,
Yes.
linear, but it's like the surface was smooth.
Yes.
There was like sharp drop in like surface.
Well, one assumption about manifold is that manifolds are smooth, right? There are many cases that these algorithms cannot capture, like if the manifold is a non-convex manifold. Say, for example, you have a manifold and you have the hole. You have the Swiss roll, for example, but there is a hole here in the data. Then this algorithm cannot does this. I mean, it's not convex in a sense that if you draw a line from one point to another point, if it is convex, the line should be included, right? Should be on the manifold. But if there's a hole here, then there are cases that you draw a line and the line is not on the manifold. In this case, Isomap is not going to do a good job. And this is not just a theoretical scenario. You know, in practice, it happens quite often because you have a sample of data, say, for example, handwritten digits. If you think about this data in high-dimensional space, this data hasn't been sampled densely from the manifold. You know, there are spaces on the manifold or on the high-dimensional space. The data is dense, and there are spaces that data is sparse. It's as if you have a hole sometimes in the manifold. And then you have problem with Isomap. But we're going to see algorithms that address this as well. Yes?
The figure with the faces where they're rotating, why didn't the algorithm find the features of the face as its principal components?
Features of?
The face, like, you know, this overall structure. Like, that's what PCA told us. Like, the first few will be just the face.
Mm-hmm.
But this one is showing that the rotations are coming out as the first axis of variation.
You know, this data has been created manually. There are only 3 degrees of freedom. Okay, in an ideal case, if you make a kernel matrix out of this, an ideal case, I'm talking. This kernel, the rank of this kernel is 3. So it's n by n matrix, but the rank is 3 because there are only 3 degrees of freedom. There are only 3 directions of variation. We made this, you know. There is no facial expression here, for example. This is the same object. We just rotated the camera horizontally. We rotated the camera vertically. So it means that all of them are exactly the same in all of the direction of variation except the view horizontally, or except the view vertically. If you do PCA might capture this, but PCA is going to find way more than 3 direction of variations. An ideal algorithm is going to find only 3 direction of variations because the data has only 3 direction of variations. So, yes?
So given the data set, how do you know if it's like nonlinear or linear? Like how do you know if it's like a curve or if it's linear?
We don't know.
Test it with
Yeah.
so much algorithm.
Right, we don't know actually. There's no easy way actually to know that it's linear or it's not linear. You can do some ad hoc tests. You can do some heuristic test. For example, if you compute the Euclidean distance between all points and you compute geodesic distance between all points, it turns out that they're almost the same. It means that it's linear. Otherwise, it's not, right? But it depends also on some parameters, you know, how you choose k. For example, if you choose k large enough, then Euclidean distance is going to be the same as geodesic distance, right? Because, yeah, if k is so large that this point is a neighbor of this point, then Euclidean distance would be the same as geodesic distance. K is small, how small it should be. You know, it's a parameter. It's not like a clear-cut answer to this, but sorry. Yes.
So data's like a manifold or something with curvature, Isomap would work better with PCA, right? But then, like kernel PCA, depending on what kernel you pass it, right? When would KPCA be better than Isomap when it comes to data on manifold? Like what kernels would be better?
Kernel PCA never going to be better than Isomap or LLE.
Why?
Because, you know, later on in this course, we are going to see that Isomap is in fact kernel PCA. And locally linear embedding that we are going to talk about after Isomap is in fact kernel PCA. But they are computing kernel in a different way. You know, there is a piece of code which computes this kernel. Because kernel, just think of kernel as similarity between points. We're computing similarity of point in a different way. The reason that kernel PCA doesn't work well is that we don't know a good kernel which basically capture the similarity between points on a manifold, which is good actually for unfolding, you know. We know good kernels for the task of classification, for example, but we don't know good kernel for the task of unfolding. So there is no closed form kernel, but there exists some data-driven kernels. And this is Isomap compute a data-driven kernel, or LLE as well. So we'll see that there is a sort of general framework that all of these algorithms that we're going to talk about is an instance of that algorithm with different type of kernels. But kernels that we are aware of, like RBF kernel or polynomial kernel, they are not going to do a good job here. And never in practice you use kernel PCA, almost never. Okay? Okay. Okay, the next algorithm actually that we are going to talk about is LLE, Locally Linear Embedding. And Locally Linear Embedding published in the same issue of Science, just as I said, back to back. So local linear embedding comes from completely different point of view. It's pretty nice intuition associated to this algorithm. The intuition actually comes from the fact that geometry of the manifold locally can be captured just by linear functions. Or a nonlinear manifold locally look like a linear patch. You know, if I just look at a small area here, it is a linear patch. Okay? So what if I capture the geometry of a local, of a small patch, a nonlinear patch, and then try to put all of these patches together in low-dimensional space? It's like piecewise regression, you know. In regression, you know how to do linear regression, but if you have a nonlinear function, in regression you can do piecewise linear, you know, you compute linear functions linearly and then put them together. If I want to unfold this, one way is to do these patches and then rotate or translate them such that they are aligned. Okay, that's what locally linear embedding does, but in a very wise way. We need to optimize two objective functions in LLE, which I'm going to show you in details. This is one objective function, this is another one. Again, we are in high dimensional space D, we want to go to low dimensional space Y. So Y is unknown. So in high dimensional space, similar to Isomap, we are going to make a k-nearest neighbor graph. So I'm going to identify for any point xi, I'm going to identify its k-nearest neighbor, these red points, and I'm going to connect this point to those points. So there will be a k-nearest neighbor graph. Then I'm going to minimize this objective function. And what this objective function is, this objective function is basically when the number of neighbors are k, is an objective function which tries to reconstruct each point xi by its k-nearest neighbor. So give me a set of weights such that point xi can be reconstructed by its k-nearest neighbor. So point xi has k neighbors. So I would like wi1 times xi1, when xi1 is the first neighbor of x, plus wi2 times xi2 plus wik times xik. I want this be approximately xi. Okay? So I need to reconstruct each point by its k nearest neighbors. So I need to optimize this objective function, or I need to minimize this objective function, which each point has been reconstructed by k nearest neighbor of that point. So the unknown is w. So weights are unknown. I don't know which weight to choose. But suppose that we solve this objective function and we do know the weights. Okay? Now I go to another objective function. The second objective function looks like similar to the first objective function. But in fact, just the form is different, because here x is known, w is unknown. Here w is known, but y is unknown. So the same set of w that I computed in the first step of LLE, I will keep them fixed, put them here. And now I'm looking for y's. So basically in a high dimensional space, I try to reconstruct each point by its k nearest neighbor, compute w's. Fix those w's, go to p-dimensional space, find a configuration of points that satisfy the same condition, means each point yi can be reconstructed by k nearest neighbor of yi with the same set of weights. Means whatever was the structure of the points and its k nearest neighbors, I would like to preserve that in low dimensional space. So the same point in p dimension now should be reconstructed by same set of k points with the same set of weights. Okay? So here y is unknown and w is fixed. Yes?
So if P is the same dimension as the original space, will Xi essentially always be the solution? Like if we're going from
Yes. Mm-hmm. Yeah. So you haven't done anything. You're going to get back. Yes?
For k nearest neighbors, what do we use as distance?
Euclidean distance, yeah. Yes? T is data points. You know, I'm just a number of data points. I'm using the notations of the original paper. This is from the original paper. T is the number of data points, and K is the number of neighbors. So on the board and on my slides, I'm going to use the same notations that we use always. So N is going to be the number of data points. But here comes from the original paper. T is the number of data points.
So the second one, the inner estimation is straight from I to
Second one? No, it's J1 to T. Because, you know, when here actually you're computing W for the k nearest neighbor, and the W for the rest of the data would be 0. So you're reconstructing this point with its k nearest neighbor, the rest of W would be 0, right? Here actually I'm looking for Y. I don't know who is neighbor, who is not neighbor. The same set of weights, which only k of them has values and the rest are 0, can be, I can put it here, you know, and I can optimize it over all data points. But many of those points will get coefficient 0. Only k of them will get the value. Okay, question? Okay. And by the way, LLE was invented by Sam Royce, who was a very great researcher. Who unfortunately died in 2011. He was quite young when he died in 2011. He has many contributions in machine learning. Okay, local linear embedding, it's called LLE. And so the first step of LLE is similar to Isomap, construct a k-nearest neighbor. So you construct the k-nearest neighbor graph. Step 2, compute Wij such that for all I xi is close to summation of Wij and neighbors of x. So I will use this notation. So in this notation, actually, Vij is the index of the jth neighbor of xi. Yes.
Sorry, that Wij, that's supposed to be Wieij.
Wieij?
The Wi and the J should be the index of the neighbor of
Right.
X, right? So it's not actually Wij.
Why not?
Because it's supposed to be Wi, the subscript I at J, right?
It depends on how you define it. You know, J is indices of neighbors of xi.
Right.
V shows neighbors of x. So XVI is in a neighbor of is the neighbor of point xi.
Right.
And J indices which neighbor? You know, we have k of them.
Right. So I guess
And this J goes from 1 to k, and you have k of W. You know, there's nothing wrong with this type of.
W is n by n, right?
No, it's a scalar here. This W is a scalar.
Okay.
No, we haven't defined any matrix yet.
Okay.
This W is in a scalar.
Yeah. That's right.
Okay. Yes.
So different weights yield different reconstructions. How do we measure how well we reconstruct? Like, what is the loss that we're looking to minimize?
This is the loss.
Oh, just that?
Yeah. So we want to minimize this and find Wij's. In fact, we need to minimize this subject to a constraint that summation of Wij for j equals 1 to k is 1. So it's like convex reconstruction of points. So we will see that this constraint is not a unique constraint, but is important. You know, later on when we try to do this optimization, you will see that we do need a constraint for this. Yes?
Is that so the weights don't become too dominant? Like a certain weight doesn't become too dominant?
No, not only that. Let's go through the optimization. You will see that why do we need a constraint for this. Okay. So basically, that's the objective function that we need to optimize. Okay. So how can we do this? How can we find basically the set of weights for each point? So let me start with this term. So this term, the I term, would be xi minus j equal 1 to k of wij x v I j. Okay, I would like to rewrite this objective function with just vectors and matrices. You know. Okay, let me define Wi as a matrix of all neighbors of point I. So point I has k neighbors. I will just put the first neighbor at the first column, second neighbor, second column, and I have k neighbors. So what's the dimensionality of this matrix? Sorry? Yeah, it is d by k. Because points are d-dimensional and they have k neighbors. So it's a d by k matrix. Also, I define vector Wi. See, this is a scalar, but this is vector. I define vector Wi to be Wi1, Wi2, Wik, a k by 1 vector. So all weights that I need for the construction. And I also define E to be a k by 1 vector of all ones. Okay. Okay. You know, I can write this summation in matrix form using this matrix that I define and this vectors. How can I write it using these new variables? VW. So it's VW. So this is this term. Okay. So my objective function now is going to be xi minus vi wi. And w is unknown. Okay. So similar to this matrix that I had, which was d by k, constructed of all neighbors of xi, I'm going to make a matrix. So I'm going to make a matrix of this form, xi, 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 d by k. So I'm going to repeat xi k times. If I want to write this matrix in terms of E, what is this matrix is going to be?
E times X transpose.
Or xi, which is d by 1, times E transpose, which is 1 by k. So ei et would be this matrix, right? Okay. So now I'm going to claim that xi is in fact xi E transpose W. Do you agree? You know, I have this point repeated k times. I'm going to multiply each of these by a coefficient such that summation of these coefficients is equal to 1. So this is xi. 2% of xi plus 80% of xi is xi, right? So basically, xi E transpose Wi would be xi. Is that okay? Okay, let me rewrite this objective function. So with this notation. So xi would be xi E transpose Wi minus Vi Wi. That's the objective function that I would like to minimize. So this is going to be xi E transpose minus Vi Wi transpose. Just expand this norm. If you expand this norm, it's going to be Wi transpose transpose times xi et minus Vi transpose times xi et minus Vi Wi transpose. Or, yes?
I'm wondering why Wi is transpose.
It's not transpose. Okay, so Wi is not transpose. Now, when you expand this norm, it's this quantity transpose times itself. This quantity transpose would be Wi transpose times this one transpose times the quantity itself. So that's basically what I would like to minimize. So I need to minimize this. Okay, this is noun. You know, this depends on xi, on e, and vi. All of them are noun. So let me call this G. This is a k by k matrix. Let me call it G. So G is noun. and it's called gram matrix. So basically, I would like to minimize WI transpose G WI. Okay, what's the solution to this optimization problem? Yes?
The eigenvectors, like WI is the eigenvectors of the,
No, without any constraint.
of the 0.
0. I mean, if you don't have any constraint, then the solution to this objective function would be W equal to 0. You know, it has a trivial solution, which I'm not looking for. You know, I'm not looking for this trivial solution. That's why I need a constraint. And don't forget that the constraint for LLE was that summation of Wij is equal to 1. So I have a constraint here that summation of Wij is equal to 1. So it means that like E transpose Wi, E transpose is 1 by K, and this is K by 1, is equal to 1. Okay? So this is a constraint optimization problem. I can write Lagrangian for this. So Lagrangian in terms of Wi and a dual variable lambda is going to be Wi transpose G Wi minus lambda E transpose Wi minus 1. Take derivative of Lagrangian with respect to primal variable Wi. This is quadratic. W transpose GW. Derivative with respect to W would be 2 GWI minus, take derivative with respect to lambda, with respect to Wi, it's going to be minus lambda E. Okay? So that's it. This should be equal to 0. Okay, it means that 2 GWI is equal to lambda E, and it means that GWI is equal to lambda over 2E. E is noun, G is noun, Wi is unknown, right? And lambda is unknown. If lambda is noun, you can compute Wi, right? Just multiply both sides by the inverse of G. So if lambda is noun, we can compute Wi. But the lambda is unknown. What can I do? Suppose that I choose a wrong lambda here, what's going to happen? The solution for Wi is lambda over 2 G inverse E, right? A wrong lambda is going to scale W wrongly. But it doesn't matter because the summation of Wi is 1. Set lambda arbitrary, just to any value. Solve for W, normalize W. Make sure that summation of W is equal to 1, right? Okay. So we can solve for any arbitrary lambda, and then normalize Wi such that its sum is equal to 1. Okay? So when I was asking about optimization, you said that the solution would be eigenvectors of G. If I change this constraint, this constraint is E transpose Wi is equal to 1. If I set the constraint that Wi transpose Wi is equal to 1, means that the length of W is 1, then you are right. The solution is eigenvectors of G. And it doesn't matter, you can do LLE that way, but LLE is traditionally has been solved this way, right? Yes?
Is G always invertible?
Sorry?
Is the gram matrix always invertible?
The gram matrix is invertible or is not invertible, depends on the number of K that you are choosing and dimensionality of the data. So you have K points in D-dimensional space. If D is larger than K, this K by K matrix is most likely full rank and is invertible. But if K is larger than D, then definitely this matrix is not invertible, right?
So does that mean this method is not really suitable if you have too few data points?
This means that this method, this solution could be problematic, exact solution could be problematic if the dimensionality, usually the data that we work with, the D is very high, the images and so on. And the number of neighbors are less than the dimensionality. So most likely we are fine. But if that's not the case, if you choose K to be large, it doesn't have to do with N. It doesn't have to do with having enough number of data or not having enough. It has to do with D, dimensionality of even if you have two small number, the number of points are small, it doesn't affect G, right? What affects G is D, dimensionality of data, and K. But in worst case, suppose that this is not invertible. Just inverse this. Add a small value of identity matrix to G, then it's full rank. And so you can always find an optimal solution here. Find P inverse of G, right? But yeah, it's going to be problematic in the case that K is larger than D. Okay, any question? Okay, so let me show you a couple of examples. Actually, we haven't done the second objective function. We have another objective function that we need to solve. Basically, we need to fix the W that we are computing here and then solve another objective function in terms of Y. When it's Yi, Wi is fixed and Y needs to be computed. So it looks like the same, but as I said, the unknown is different and the solution is completely different. So we're going to do that in the next lecture, but let me show you an example. This is the example that you work with and you run PCA, and you have seen that when you're running PCA, points get mixed up, right? Because PCA is linear. But if you run LLE on this, that you're going to do in your next assignment, then you will see that points will not get mixed up, okay? And basically, as if this manifold has been unfolded. But LLE does not preserve the shape of the original manifold. This will be distorted, you know. If you have this manifold, it's not that the scale of the manifold in low dimensional space is going to be preserved completely. So you're going to see, if you look at the scale carefully, you will see that the y-axis and x-axis are almost the same, regardless of the fact that how long the original rectangle has been, you know. It will be mapped to a square. And we'll see the reason for that later on. These are a couple of examples of nonlinear manifold that has been mapped to low dimensional space nicely using LLE. And that was in the original paper that I showed to you in the first lecture, when this path, for example, captures this face expression related to sadness or happiness. It's another example of the original paper when text have been mapped to lower dimensional space. And if you look at this cloud of data, these points semantically are related, like fought, fighting, capture, killed. Something important, you know, this is another example which shows the difference between PCA and LLE. You know, the data set is one single point of faces, the noisy data set that you work with without noise. It's a Brandon Fry face. So this has been, you know, it's on a background. It has been shifted horizontally and vertically just by 1 pixel at a time. So this is the picture. Then you move it on the background by 1 pixel, this another data point, and so on. And you do it vertically as well. This is the whole data set that you have. If you run PCA on this, these are the nodes that you're going to get in PCA. But if you run LLE on that, these are the nodes that you are going to. You see that the structure of manifold has been preserved way better, you know. Basically, smoothly, it shows what happened. K, as I told you, is a parameter for Isomap and for LLE both. If K is small, the graph is not going to be fully connected. And you have problem. The graph should be fully connected. Okay? So if you choose a small K, I'm going to run LLE in the next lecture and show this to you exactly. But if K is very small, then the graph is not fully connected, and then you have problem. This is the case. With a wide range of K, it does a decent job. Like this is K equal to 6, 8, 10, 12, 14, and all of them are decent. This is K equal to 20. Look at K equal to 30. What happened here?
The surface rolling up.
Sorry?
The surface kind of starting to roll up.
Yeah, again, you know, these points are mixed up, right? As if it has been rolled up. And the same for K equal to 40 or K equal to 60, you know, is a mess. You know, all of these points are mixed up. If K is large, both Isomap and LLE approaches to PCA. You know, when you want to reconstruct a point by 60 neighbors doesn't form a local a linear patch anymore. You know, it's a curvature. But you're approximating this curvature by a linear patch. And then as if you're, you know, collapsing all of this point to a linear surface. So it's not going to work nicely when K is large. Any question? Okay, see you on Thursday.